Hello, welcome to an introductory lesson on simplifying radicals. We have this symbol, oftentimes there's a little tail here, that we more commonly call square root, but it is actually known as a radical sign. For example, if we put a 25 under the radical sign, we have been taught that that means the square root of 25. And the square root of 25 is a very nice number. Square root asks what number multiplied by itself gives me this value under the radical sign. And so we know that 5 multiplied by itself or negative 5 multiplied by itself could be the answer to the square root of 25. Now there is a special name given to that number under the radical sign, and it's called the radicand. In my experience, that word is very seldom used, but it is used in your textbook. So if they talk about the radicand, they're talking about this number right here. What is it that's under the radical sign? Now, this radical has a nice whole number answer. It's either 5 or negative 5. But we can have mixed radicals. A mixed radical, oh wait a minute, next one is like radicals, are two radicals that have the very same radicand. And so, for example, we would have to look at mixed radicals to talk about two different radicals that are like radicals. And what I mean by that is a mixed radical can contain a rational number that just is all negatives, all positives, all decimals, fractions, all of those numbers in the rational number system. And so a root 7, now there's no nice answer to that. It's some decimal value that would have to multiply by itself to get you a 7. But I could talk about having two of those root 7s. And then this would be a mixed radical. And 2 root 7 and perhaps a negative 3 root 7. We have a rational number multiplied by a radical. And so that entire thing, that entire negative 3 root 7 or negative 3 radical 7 would be considered a mixed radical, and both of these would be considered to be like radicals. So these are like radicals because we have this radicand and this radicand under my root sign. Having trouble making some brackets there. These are the same radical. So the big idea there is that like radicals contain the same radicand. They can have a different rational number out front, but they are considered to be like radicals. And that will become important when we're adding and subtracting radical values. Okay, when we talk about radicals, there is a certain amount of keeping track of what's under that radical sign because we want to be able to fully reduce radicals. And so we always keep an eye out for these values that are perfect squares. Perfect squares, you put them under a radical sign and you get a nice whole number value out of that. 1 times 1, well, that's an easy one. 2 times 2 is 4. So 4 is a perfect square because it has a nice square root value. 3 times 3, 9, 16, 25. Finish up that list because those we're going to want to be keeping a close eye out for. That should be 6 squared. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. 121 is 11 squared. 144 is 12 squared. 169 is 13 squared, 14 squared, 196, and 225. That is, I mean, we can continue going, but that's the list that you would be expected to have mentally as all of the possible perfect squares with nice whole number square roots. So most of you have these ones. Make sure that you've got these ones mentally practiced so that you can take a quick and nice easy square root of perhaps say 196, and you can tell me it's, oh yeah, that's 14. For example, if I ask for the square root of a perfect square, there it is, 144, that's one of my perfect squares. It has a nice answer because it is made up of a 12 times a 12, or a negative 12 times a negative 12, but let's just consider the easy positive answers there. So the answer is 12. 12 multiplies by itself to get me that 144 because it is a perfect square value. My 144 is one of those nice perfect squares. We can take the value of the answer when it's not such a nice perfect square, but for this we would need to get a calculator involved if I wanted to get if I wanted to be confident of my answer. But I know I could mentally ballpark that because the square root of 4 is a 2, and the square root of 9 is a 3, and the square root of 16 is a 4, and so the square root of 10 is between this 9 and 16, so it's 3 decimal something. And in fact, if we do the square root of 10, then we find out it's actually a 3.162 and a bunch more decimal values, and we would have to multiply that by itself to get to 10. Now my calculator has truncated that answer. It actually isn't, there's more little bits and pieces that I would need in order to be able to actually get back to an accurate 10. So we would say it's approximately, and we would choose to round it to some level of accuracy. Let's call it 3.16. Now, this is something I want to talk about here. The square root of a negative number. So you want to tell me what number multiplied by itself gives me a negative. And that has no answer in the real number system, because in order to create a negative value, we have to multiply a positive times a negative to get a negative. And in fact, if you ask your calculator, hey calculator, what is the square root of negative 25? It tells you that there is no answer in the real number system to that. So we cannot take the square root of a negative number. Now something like this just means, hey, I have a 3, a normal 3, multiplied by the square root of 16. So my normal 3 would multiply by the 4, which is the square root of the 16, which is a 12. Here, I want to illustrate that we can do operations under that radical sign. A 38 plus an 11 comes out to 49. And so we can be asked to do more and more and more inside a radical before we actually simplify it. This is 2 times the square root of 49, so 2 times 7 gets me 14. And similarly, we'll be doing some things where we are multiplying radicals here. And if I'm multiplying the square root of 3, multiplying it by the square root of 12, I am actually allowed to pop those both under a single radical sign, because there is a nice easy answer to that. My calculator knows that if I do the square root of 3 times the square root of 12, whoops, let's back that up, square root of 12, then we get a nice easy 6. Why do I get a 6? Well, because multiplying them by each other under that radical sign gets me that square root of 36, which is a nice 6. So we'll be doing some operations with radicals. Finally, down at the bottom, just talking about some variables under my radical sign and simplifying radicals. I should never leave this as a final answer when I'm working with radicals. Just like on a test, you would never leave me 10 over, let's say, 4, because that fraction can be reduced. And so you would say, okay, well, divide out the 2, divide out the common factor, because that's what fractions are all about here, top and bottom, the different factors, and I would get 5 over 2, and that is my fully reduced fraction. Well, similarly, this radical isn't fully reduced because I have one of these nice perfect squares hiding in that radical. Just so happens there is a factor of 25 in a 50. And so to fully simplify this radical, you would multiply your 25 times your 2. Well, that's still a 50 under my root sign. And just like if I can put two radicals together into the same, under the same radicand, I can go backwards and break it up into two separate radicals. And so simplifying this radical, I would say, well, that's the same as the root of 25 multiplied by radical 2, or the root of 2. Now, there's no nice answer to that. That's some decimal value. And so I can reduce this radical. Now, it's important to realize that these have the same numerical value. So this is fully reduced. And if I check out on my calculator, what is the square root of 50? It is some rotten rounded decimal of 7.07-ish. And so a radical 50 is approximately a 7.07. Let's just check out 5 times the root of 2. What is it approximately? Well, 5 multiplied by the square root of 2 is that 7.07 again. And it should be, because they are identical value, just like your 10 over 4 has identical value to your 5 over 2. They would both be 2.5 under or if you put them through a calculator. These are identical values here, but they are different versions of that same value. They are the fully reduced value of the radical 50. Now, when I introduce the idea of variables into the mix here, you want to think abstractly here, because these, remember, variables are just holding the place for a mystery value. And so when I hold the place for a mystery value, x could be anything, but I'm squaring it. So let's say it's 9. Well, I've got 9 squared. And so 9 squared would be an 81, and the square root of 81 would be back to that 9. And so anything I square, any mystery number, would end up being that mystery number multiplied by itself. And so what is the square root of x squared? Well, it's x. What number, or what value multiplied by itself gets me x squared? Well, x multiplied by itself would get me that x squared. And so if we put a rock solid set of numbers, for example, let's use that, let's x be a 9, then I would have square root of 9 squared, we would get the square root of 81, and we would be back to the 9, the x that we originally started with. And so when we are finding the square root of our variables, we can just say that the square root of x squared would be my x. Now, square root of 32 x to the exponent 4. Well, 32 x to the exponent 4, first of all, when trying to reduce 32, I look to my list of perfect squares. What perfect squares are in a 32? Well, there is a 4 in a 32. However, that's not the, sorry for the interruption there. 32, that's not the largest perfect square in there. The largest perfect square is actually a 16. And so if you pick the largest one, then you'll fully reduce it in one step. If you pick a smaller perfect square, you'd have to take out another perfect square later. And so that 32 could be a 16 multiplied by a 2. And my x to the exponent 4, what value multiplied by itself? Well, it would be x squared multiplied by itself. That would get me my x to the exponent 4. And so if I break this up, my square root of 16 times my square root of 2 times my square root, I'm going to put this back together here because I'm going to go to that answer. So I've got a 4 multiplied by that square root of 2 multiplied by an x squared, because the answer to the square root of x to the exponent 4, I can see that the identical value multiplied by itself is an x squared. And then this is no longer under a radical sign, so let's bring that out with my 4x squared times the square root of 2. This is the fully reduced version of my original radical. I pulled out that nice perfect square and showed its whole number value. And I pulled out the square root of x to the exponent 4. And I had to leave in that radical 2 because it doesn't have any nice perfect squares in it. And so we get to something like this, a to the exponent 7. And you might be looking at that saying, well, nothing multiplied by itself gives me an a to the exponent 7. So this is where I would break it up into, well, an a to the exponent 6 multiplied by another a. That's still a to the exponent 7 because I would have one of them here. And this does have a nice square root. A to the exponent 6 times that radical a. If they're both under the radical sign, I can liberate this one. What value multiplied by itself? Well, an a cubed multiplied by an a cubed gives me a squared. And I would have an a left over. Maybe I could even show that in an extra step. Show that in my under this radical sign, I'm going to leave this one alone because I can't do anything with that, an a cubed multiplied by another 3a's. So I would have 3a's multiplying by 3a's. I would have 6a's. And so the value that multiplies to give me my a to the exponent 6 would be an a cubed. So the square root of a to the exponent 6 is a cubed. And that is the fully reduced version of an a to the exponent 7. Our last one here, square root of 27, x to the exponent 6, y to the exponent 3. So I get busy thinking, okay, which of my perfect squares is hiding in a 27? Biggest one here, or the only one, is a 9. 9 times 3 is 27. So I'll break that guy up into a 9 times a 3. There is a nice square root to x to the exponent 6. It would be an x to the exponent 3 times 3. But this y cubed, there's no nice square root to that. So let's take out a y squared, because we can find the square root of y squared multiplied by another y. That's still y cubed under there. So let's pull our nice easy ones out front. So there's a nice answer to that 9. There's a nice answer to that x to the exponent 6. And there's a nice answer to that y squared. But there is no nice answer in terms of an easy square root of 3, nor y. And so a 3 times 3 gets me my 9. An x to the exponent 3 times another x to the exponent 3 would get me my x to the exponent 6. And the square root of y squared, very similar to the square root of x squared. Square root of y squared, well, it would be a y times y would give me y squared. And I would still have these 3 and y that are locked under that radical sign because there is no nice, easy, square rootable answer to that. And so this is the fully reduced answer to my original radical under that square root sign. So now what you need to do is to work on your worksheet of riddle sheets. We have got the first one deals with nice easy square roots. Now some of these are in fractional form, some of them are in decimal form, and so they're a little beyond some of the examples, but what I would like for you to do is to think about those and see if you can come up with a nice easy way to justify those answers. Simplify the expression, write the answer of the exercise or the letter of the exercise in the box above its answer. So once you find the answer to R, you'll look down here and put an R above its answer. Then we get into taking the square root of values that are all fully square rootable, if that's a word, and we have no radicals left. On the back, not so much. We will have practice reducing these radicals. So what you always want to do is keep handy your list of perfect squares to be finding those perfect squares hiding under your radical signs. And then fully reduce mixed radicals. So here I would have a normal 2 multiplied by a root 18. Well, there's a nice 9 and a 2 under there. And so I would have a nice easy answer of 2 times 3, root 2. And so my fully reduced radical there, 2 times 3 is the whole number 6, root 2. And then I get busy finding that answer in my answer column, put the letter A in box 18. I believe that's what we do. Yeah, some of these we get rid of them, but these ones we match up, and so on. It gets more and more complicated as we go, but what you want to do is be fully reducing all of your radicals and finding the answer to the riddle sheet. Remember to find the answer to the riddle. What did Dr. Drone say to the guy who thought he was a $100 bill? The answers are cute, but the value in it is to check your math, to see whether you're actually finding a legible answer, to see whether you've matched up the different mathematical answers with your questions. And then we'll see you on Monday morning.